look at the different types of probabilities, and there's three main types that we look at. There's your classical probability, your empirical probability, and your subjective probability. What we do is we use, let's say we let E be the event, then we write the probability of E like this. So we use P parentheses E. This doesn't mean anything is being multiplied here. It stands for the probability of event E. So that's the notation we use. It doesn't mean that P is being multiplied by E. Now your classical probability or your theoretical probability is used when each outcome in a sample space is equally likely to occur. We call this classical because you tend to see this in classic examples like from a deck of cards or rolling a die. So something that has a very set probability that you can always figure out. So that would be your classical. And you can see your examples here. Now, how do you find your probability? And it actually occurs for all these three the same way. Basically, it's just a proportion. You're pretty much looking at your part over your total. That's how we find probabilities. It's really the same thing as a proportion in statistics. So I guess more of a ratio, right, in math, but a proportion in statistics. So you look at the number of outcomes for event E, and you divide it by the total number of outcomes for the whole sample space. So how many ways can you get event E versus all the ways altogether? So let's look at event A. Let's say you have our 6-sided dice again, and you roll a 3. So if you roll a 3, well, there's only one way to roll a 3, right? You either get 3 or you don't 3. So the probability of event A, there's one way to roll a 3. And then there's 6 possible things that could happen there, right? If you have a 6-sided die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. So that's your sample space. There's 6 options. So there's 6 total options. There's one that we're looking for. So your probability here is just 1/6. Now we tend to like decimals a lot, so I'm going to round this to 3 decimal places and use that as my answer. Now we tend to like decimals, but if you want a percent, this would be 16.7%. So you have, almost 17% chance of getting that 3. What about rolling a 7? This is event B. Well, we know the sample space is 6. Is it possible to get a 7 on a 6-sided die? No, right? There's no 7 on there. So if we're just using, again, one 6-sided die, there's no possibility of that happening. So your probability there is 0. And then for event C here, rolling a number less than 5. So you could roll a 1, a 2, a 3, or a 4 there. So the probability of event C occurring, well, there's 4 ways to get this to happen, and there's 6 possibilities altogether. So we get here 2/3, which is about 0.667. Okay, so this is your classical probability. Again, these tend to be things like we know the probabilities for like die, cards, et cetera, that sort of stuff. But you're still just using this idea of part over total. The second type is called empirical or statistical probability. This tends to be based on observations, or I like to think of this as like real life data, that you have an experiment or a study and you have this real life data. That's how we get these values here. So it's still the same idea of part over total. In this case, it tends to be the frequency is our part here. Okay, so how many times the event occurs in the study. So a company is conducting an online survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So far, 1,490 adults have been surveyed. And the pie chart here, this is also in your text, so you can read it there in color, shows the results. And just as a note, digital books include ebooks as well as audiobooks. So what is the probability that the next adult surveyed read only print books during the last year? So only print books. So let's call this event A. Okay, so what's the probability of event A? Well, how many options are there for print books? So let's see if I read through here. Read only print books is 578, right? So that's the number for the event that we're looking for. And then on the bottom, we want the total. So what I'd have to do here is figure out, well, what's 578 plus 395 plus 426 plus 91. And I'm going to add these all up together and I get that 1490, which is what we saw right here as well. Okay. Now you definitely use your calculator here, and I'm going to round to 3 decimal places, and I get 0.388. So about 38.8% of adults read only print books last year. So in probability form, again, we tend to like the decimal version, 0.388. So again, it's always part to total. What's the part that you're looking for? So here we're looking for only print books, which is right here, only print books, over that total. So even though it's a different type of probability and it uses real world data, it's still that same idea. All right, let's do one more together here before we look at the next type. It says a company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 site users have been surveyed, and the frequency distribution shows the results. What is the probability that the next user surveyed is 23 to 35 years old? So this is my event. Let's call it event A. So the event A is that someone chosen is between 23 and 25. Well, how many people are there between 23 and 35? There are 312. Okay. How many people are there all together? If I add these all up, sorry, let me check my notes here. I see that the total should be 975. So I'm just using this idea of part to total. And when I go ahead and do this, I believe it comes out exact. Let me just double check my notes. Sorry, guys. Yeah, we actually get exactly 0.32. So this is the probability that someone or the next person being surveyed would be between 23 and 35. So we say the next person being surveyed, but really just in general, the probability that we chose someone who is 23 to 35 is about 32%, so 0.32. Now, what we do see is that as you increase the number of times a probability experiment is repeated, the empirical probability, which is the relative frequency of an event, approaches the theoretical probability. This is known as the law of large numbers. So what does that mean? It basically means that the larger your sample size is, the closer you get to the true probability, right? When we have real world data is messy. If I only have a couple data points, it really doesn't give me a good picture. The larger my sample size, the better and closer I get to actually having the true probability for that population, is what we're saying. So as an experiment is repeated over and over again, so again, larger and larger sample sizes, the empirical probability approaches the actual probability of the event. So that sample size data, the larger and larger and larger and larger it gets, starts getting closer to the population probability. So it becomes more of a true probability, not just based on a sample, the larger it gets. This is called the law of large numbers. And here's just a quick example of that. So as an example of this law, suppose you want to determine the probability of tossing a head with a fair coin. So a fair coin is just a standard coin. It means like it's not weighted. It's 50% chance of heads, 50% chance of tails. So you toss a coin 10 times and you get 3 heads. So you obtain an empirical probability of 3/10. Because you toss the coin only a few times, your empirical probability is not representative of the theoretical probability, which is 1/2, right? So when we toss a coin, it's a 50-50 shot if you get heads or tails. That's a 1/2 probability that you would get heads. Because you only did it 10 times, you got 3 heads. Your probability is too low here. It's not accurate, right? But if we do this over and over again, we do this lots more times, then we do see it starts to even out. So the scatter plot here shows the result of simulating a coin toss 150 times. So this is the number of tosses versus the proportion that are heads. And you can see that over time, you do start to hit that 0.5. So here, with your first toss, you may have had kind of varying probabilities because you don't have too many tosses yet. But as you do more and more tosses, you're starting to see that 50-50 split, right? Maybe you have, 49 heads and 51 tails, right? You start to get a little bit more even than in your beginning examples. So that's what this is saying here. The more you do something, the larger that sample size is, the closer you get to those true probabilities.